Hi everyone, my name is Suman Karumuri. Today I'm going to talk about KalDB, a Kubernetes native log search platform. My pronouns are he and him. So in this talk we are going to look at the motivation behind KalDB, and then we'll talk about the architecture of KalDB, and then we'll talk about how KalDB solves those problems. So first, a little bit about me. I'm currently a senior staff engineer at Slack. I work on observability and performance. I love building petabyte scale observability systems. In the past, I've built systems in all three pillars of observability. In log search, I manage like Elasticsearch cluster at very large scales for a lot of companies. I wrote an in-house log search platform called Loglins at Twitter 7 years at this point ago. And on the tracing front, I was the tech lead for Zipkin project at Twitter, and I was also contributed to the open tracing spec. And I've built end-to-end tracing pipelines at Pinterest and Slack. On the metrics side, I've managed several large clusters running OpenTSDB and Prometheus, and I've also built in custom storage engines, Viz at Twitter, UV at Pinterest, and we wrote a recent research paper called Mark. Please check it out if you have some time. In general, I love building infrastructure and distributed systems. So let's jump in with the motivation for KalDB. So just a little bit of overview. Logs are widely used for monitoring our systems. They're used for triaging issues, debugging issues, and fixing them. As a result, centralized log search platforms have become one of the most essential pieces of modern day systems infrastructure. So one of the biggest reasons we need centralized log search is in this cloud native world when machines can come and go anytime, or containers are being spun up and spun down anytime. Centralized log search systems aggregate those logs into a single location and provides guaranteed retention for those logs beyond the lifetime of the machine or the container. That is one of the biggest features centralized log search systems provide. They also provide other advantages. For example, they help you triage issues across machines, across services, etc. Further, these centralized log search systems also provide you consistent experience for querying your logs that are probably produced in different formats and things like that, but they let you access those logs in a unified format. So with that said, we collect a lot of logs at Slack, and we primarily query these logs in three broad ways. Okay, the first use case is search. For example, a customer service agent gets some magic string from a customer, and he or she goes into the log search system, puts the magic string in, and performs a full text search. Usually this is generally a recent incident, so the queries are over like a few days to like a weeks or something like that. The second big use case is the one common use case that we are familiar with, which is aggregation. In aggregation, a developer builds dashboards and alerts off of their logs. Generally, these queries look like people are generally doing group bys and aggregations on their logs to answer questions like, hey, I'm doing a deployment. Is it actually going as planned? Is it causing any regressions? Are there any more errors than they were before? Are any of my endpoints slower than before? And so on and so on. These queries are also over days and weeks because you're generally doing week over week comparisons. So for both of these use cases at Slack, we recommend our users to use Elasticsearch. And the third big use case for our logs is actually the analysis piece. In this space, for example, a data scientist takes these logs and computes a very complex aggregation of these logs, let's say to calculate a DAU or an MAU, which involves complex business logic, right? Or they can take these logs, join them with other data sets across the company to get other useful insights, right? And these queries are often run over weeks or months because you're probably doing quarter over quarter or year over year calculations. And for these use cases, we actually recommend that our users use our data warehouse. And sometimes these calculations are actually available in real time or needed in real time. For those use cases, we recommend users to use pre-aggregated metrics platform for those use cases. So what is the current architecture of log search at Slack? So today, our log search platform consists of Elasticsearch 7. We run over about 100 clusters running across 3,000 plus machines. And we recommend our users use Data Warehouse for long-term analytics. Currently, we manage about a petabyte of data, and the retention is somewhere between 7 and 9 days depending on the data set. We ingest about 4 million messages per second, which is actually only half the number of messages we produce. And we query our log data with over 1 million queries a day. The architecture of our log ingestion platform looks as the image here. So we have a common platform called Neuron, which aggregates logs from all the applications across our services and writes them to Kafka. You can also learn more about Neuron in the observability engineering book. In chapter 18, we contributed a chapter called Telemetry Pipeline Management, in which we describe Neuron. So you can read the chapter to get more information about Neuron. So from Kafka, the data is ingested into Elasticsearch via Logstash. And we have a parallel data warehouse ingestion pipeline built out of Seacore and Airflow that ingests the same data into our data warehouse. The data in Elasticsearch is accessed using Kibana and Grafana, whereas the data in the data warehouse is accessed via an in-house data warehouse UI. So here are the problems we have with our Elasticsearch cluster. There are like a lot of them. Elasticsearch is like death by 1,000 cuts, but we'll actually see 3 big problems with Elasticsearch. The first one is handling spiky log volumes. So what happens is during deploys or incidents, we often get like 10x the number of logs than we normally see. Sometimes we have control over this, sometimes we don't. For example, we launch a new version of Slack, new users, like in the middle of the night, users wake up in the morning and they're loading the latest version of Slack, and we have no control over when they do that. So we get a lot of logs, right? We get like these 10x peaks, and when this happens, our logs lag a lot, sometimes by minutes to hours. And as a result, when this happens, we lose real-time visibility into our systems. We don't know what's going on, at least from logs. Our metrics probably are up to date, right? So to actually overcome it, what we do is we peak provision our clusters, which costs us a lot of money. But peak provisioning does not solve all our problems. Here is why. So if you see on the right, on my right, you'll see that even just the organic growth of our logs itself, even though so the red line is where we provisioned ES at peak. But our new normal is more users logging into Slack in the morning. So we are producing more logs, and as a result, we have actually lagging again just because of organic growth. And again, this is something we have no control over, so this turns into like an on-call issue where you have to scale the cluster. The second big problem we have with Elasticsearch is high operational overhead and on-call load. So currently at our scale, cluster-wide operations takes days to weeks to run, and generally they impact read and write performance of the cluster when they happen, and they sometimes affect the stability of the cluster. Further, managing 100 plus clusters to keep them all consistent and performing well is a tedious and error-prone job. We often have to write software that manages the software that manages Elasticsearch. So this kind of meta management software is kind of hard to write. Then the bigger problem with Elasticsearch, even when these are not the issues, is Elasticsearch seemingly has these single points of failure that stop the entire ingestion or delay the ingestion. So what happens is, let's say you have a slow shard or you have a single node that's failed, it kind of delays the ingestion, and now you have your logs are lagging. As a result, you don't have like real-time visibility again. While rare, we have seen cases where sometimes we have data or metadata corruption, which leads to data loss in Elasticsearch. This is very rare though. And the third big problem with logs is missing logs because of field conflicts. For those of you who are not familiar with the field conflicts problem, let me give you an example. Let's say there are two developers. One developer is writing an account ID field, is logging an account ID field as a string. The other developer logs the same field as an integer. What happens in Elasticsearch is, let's say these two logs make it to Elasticsearch. Elasticsearch, depends on which log you get first, assigns the field type of that account ID field to the type it gets first. Let's say the string field gets to the log search engine first, so the account ID is a string. And what Elasticsearch does is for the next log where the account ID is actually an int, it actually silently drops the logs. This leads to lots of developer confusion because let's say you're a developer, everything is working fine. Tomorrow, some other person writes the same field in a different format. Now your logs are not there anymore. And Slack has hundreds of developers working across millions of lines of code, and this can happen anywhere in our system, and it is super hard to control. This also used to lead to mapping explosion. So what we actually did is we used to get a lot of on-call overhead too. People used to say, hey, like I'm writing these logs, why can't I see them? And often it turns out to be an issue because of field conflicts. So what we did is we did like a bunch of work to institute strict schemas in the logs we produce from our applications. In strict schemas, you actually set the type of the field when you produce it, so users cannot, it's basically a logging library that also ensures that the fields are of a certain type. So this adds another layer of schema management to users, which slows them down. But while this is a good solution that works reasonably well, there is one downside to it, which is that we only can do this on some parts of the code we control. For example, there are large parts of our logs that we don't control, that are produced by systems we don't control, like third-party software or open source software, and field conflicts are still an issue in these systems. So in summary, managing Elasticsearch is actually like managing like a race car, you know, because Elasticsearch is designed like a race car. So it treats any loss of availability as a disaster, so it stops like ingesting logs, right, and delays them. And usually the solution to overcome most of these problems is to scale it up. So for stability, we often trade off cost. So cost becomes a secondary concern when you're running Elasticsearch. Further, just like a race car, Elasticsearch needs a lot of babysitting and needs a lot of sustained investment to keep it healthy, up and running. Finally, scaling Elasticsearch is not trivial. It's very hard, and you need to know what adding more capacity does to the cluster, and you need to do it in a very diligent fashion. So it is very usually a hard problem. So, but what we want instead is something like a regular car, you know? At our scale, if one node is down and you can't ingest like 0.01% of my logs, it's okay. It's an inconvenience. Yes, there is this one case where I cannot find that one log that one machine produced for the next 5 minutes, but it's not the end of the world, you know? And cost controls are extremely important in this space because your log search system does not produce any revenue for the company, so it's a cost center. Spending more and more money on it is not gonna be good for the bottom line. Further, we do not want to do a sustained level of investment into these systems. We just want a sporadic investment into this system. And we want the system to adapt to the conditions. Finally, we want a straightforward scalability story for our log search platform, as opposed to a convoluted one, which actually needs expert intuition to run these systems. So let's look at KalDB. So we had these goals, and we translated all these like abstract ideas into a few goals. So one of the things we actually did with with our system is we wanted tired availability. What does that mean? So let's say if a log is produced, we want it to be searched within under a minute of generation end to end. In case we miss that window due to a failure or whatever reason, we want the older logs to be available under 5 minutes. Why is that important? Why do we want to prioritize fresh logs over older logs? The reason is this. You see the table here. You can see that a majority of my queries for the last 1 hour, like 93% almost, are for the last 1 hour. So if you are, let's say, behind by 4 hours, very likely the log that you ingested is probably not going to be queried ever. So spending time ingesting older data when you are not having fresh data is actually problematic. This is why we want to do tired availability. The other problem we want to solve is friction-free migration, friction-free ingestion. What does this mean? So if we get log spikes, we want to ingest the existing capacity of the logs without lagging. And we want to do this by enforcing quotas and rate limits and so on, and features like that. The other thing we want to do with ingestion is we do not want we do not want dropped logs because of field conflicts. So that's the other problem we want to solve. Further, we want to have a higher ingest rate than what is currently possible with Elasticsearch, so we can actually ingest more of our data. We obviously want longer retention. So instead of current 7 days, we might want something like 30 days. We also would like to have reduced total cost of ownership. It kind of has two components to it. One is developer time, and the developer time consists of the amount of time our team spends managing log search, and also the amount of time the developers spend trying to use the log search system. We want to minimize that too. And further, obviously, we want to reduce the infrastructure cost of the system. So the architecture of KalDB looks something like this. Just like before, you have an application whose logs are gathered by Neuron, and those logs are written to Kafka, right? The first component in KalDB is the preprocessor. The preprocessor does 3 things. It formats the logs, enforces quotas, and routes the data to a specific Kafka partition. From this Kafka partition, the indexer takes over. It indexes the data into a Lucene indexer. Periodically, it snapshots the data into a deep store like S3, and it can also serve live queries against the data it indexed. The cache node is another component in our system which downloads the data from S3, the older data from S3, and then it can serve reads against that data. Finally, the query service is our client-facing component, which actually handles all the client queries. It gets all the client queries, performs scatter-gather queries from the indexers and the cache nodes, and responds to the client queries. And the final component in our architecture is the cluster manager. It is the brain of our system. It uses Zookeeper to persist the data to a data store, and it also uses Zookeeper as a notification store. A cluster manager basically has 3 jobs. It does snapshot management, which basically means once an indexer publishes a snapshot, it assigns them to the cache node. The other thing it does is data lifecycle management. It basically means that once the data reaches its retention, let's say 7 days, it unloads that data from the cache nodes and then deletes that data from S3. The final thing that the cluster manager also does is node management, which is whenever a new node joins or leaves the cluster, it basically makes sure that the work assigned to that is handed off to someone else, or if the node is free, it gets some work to do, and also ensures that the node is actually doing the work. So overall, this is the disaggregated storage architecture that KalDB implements. It provides some standard features like separates compute from the storage. It also separates durability of data from storage. What does that mean? So the durability of unindexed data is maintained by Kafka, and the durability of the data that is indexed is maintained by S3. The system itself is not responsible for, it is responsible for ensuring that all the data that is produced is indexed and is searchable and is available, but it's not responsible for ensuring the durability of the data. For example, if you turn off all the nodes in KalDB, the data is still there. You don't have data loss. You have other problems, but not data loss. The other thing with KalDB is it's horizontally scalable. Currently, we deploy it and run it on Kubernetes. And it has minimal dependency on components. So a node coming or going does not affect the other components in the cluster or their performance. So let's zoom in on that durability a little bit as part of the recovery feature in KalDB, right? So as I said before, the indexer does three things. Indexer takes the data from Kafka and indexes into a Lucene index, right? It periodically snapshots the data into a deep store and it serves queries. And while doing this, it is actually using the Kafka partition as a write-ahead log. What does that mean? Let's say you have the Kafka partition. It has messages 1 through 100, and you have the indexer, and the indexer is index 1 message. Let's say, boom, like the indexer is gone for whatever reason, right? So a new indexer takes its place, right? And it realizes, hey, I'm too behind. I cannot catch up, right? So what does it do? It actually creates what is called a recovery task that says that, hey, I cannot index messages from the Kafka partition 1 through 99. So I'm going to create a recovery task. Here it is, cluster manager, and then I'm going to start indexing at 100. This is how KalDB prioritizes indexing fresh logs over older logs. So what happens to the recovery task? The cluster manager brings in a new indexer called a recovery indexer. What does the recovery indexer do? The recovery indexer is same as the existing indexer. It indexes the logs from Kafka and then uploads them to S3, but with one crucial difference. The indexer only has a single thread, which is enough for handling all the ingestion needs. But the recovery indexer is multi-threaded. It can actually ingest the data 10 times faster than the indexer. So it can actually catch up about an hour worth of data in under 5 minutes. So this is how a recovery index, so what the recovery indexer does is it picks up the recovery task, indexes the data, uploads it to S3, very simple. So one of the key things about this architecture that is actually good is when we are behind, we are actually adding additional capacity to the system to catch up, as opposed to taking capacity from the existing system, which is a very important property. And KalDB uses the same mechanisms when we have log spikes. When we have log spikes, we can create recovery tasks and then recover from that. So let's talk about another feature of KalDB, multi-tenancy. So currently, what we do is we have about 100 Elasticsearch clusters. Why do we have them? One reason is we have production, dev, and then like multiple like AZs and all of that, multiple regions and all of that. That's one reason. But the other reason is generally co-locating a very large log search customer with a smaller log search customer is actually an anti-pattern. The reason for this is follows. Let's say you co-locate a large customer and a small customer on the same cluster. And let's say either the log search customer is the larger customer is producing a lot of logs, writes, or they're doing a lot of reads because they're an incident or something. In both of these cases, the smaller customer is affected. To actually prevent this from happening, you give the smaller customers their own cluster and isolate the larger customers, and so on. You can do this across multiple customers, and you'll end up with multiple clusters, right? But while this is good for the customers, it actually creates a lot of overhead for the team managing these clusters, right? And this is why we have to build that meta management layer. So what we're going to do is in KalDB is we want to kind of solve that problem by providing built-in multi-tenancy. So what does multi-tenancy mean? So what the separate clusters are providing is they're providing us this isolation between data for different services without running a separate cluster. So how are we going to do it? Let's say you have two services, a yellow service and an orange service, right? A preprocessor takes these logs and we allocate specific partitions to specific services. So it writes the yellow blocks to Kafka partition 1 and the orange blocks to Kafka partition 2. And the indexer, because it's tied to a Kafka partition, indexes like the data. So indexer 1 gets the yellow service logs, indexer 2 gets the orange service logs. And finally, and when you get a query for the yellow service, they only hit the indexer 1, and when you get queries for indexer 2, orange service, they only hit indexer 2. This is how KalDB achieves multi-tenancy. Finally, this is how we achieve horizontal scaling in KalDB. Each assigned indexer has a fixed ingest capacity. So the number of indexers we bring up is we take the total ingestion capacity we are going to have, and then we divide that by the capacity by each indexer. That's the number of indexers we have. And similarly, to determine the number of cache nodes, we get the number of snapshots, divide that by slots per cache node, and then that's the number of cache nodes. And depending on the read volume, the CPU and memory allocation is allocated to these nodes. Finally, a few more features of KalDB. The way we handle field conflicts in KalDB is for the known fields, you can set the types of the data that is being ingested. And for the unknown fields, we currently index them as a string. This is not optimal, so we are actually looking at other approaches to do this, but this is the system for now. And in addition, because we control our own Lucene, we can actually do additional lower level optimizations in Lucene that make more sense for log search, but not for other Elasticsearch use cases. For example, we sort all the logs by timestamp. We also have additional parallel search capabilities in our Lucene implementation. We also have a feature called on-demand snapshot hydration, wherein on the cache tier, we only keep 1 day worth of snapshots. Because as you can see from like if you remember the table before, almost like 99.8% of our queries are for last 1 data. So this helps us handle all the 99.8 queries, 99.8% of queries. For 0.2% of queries that we cannot handle, only when a user requests the logs, we restore those chunks, and then we query those logs. The advantage of this is you can actually cut down the cost of your system by quite a bit. So we also apply lightweight standardization on our logs on ingest. So we convert all our logs to a standardized format called a span event format. One of the features, there are several features that I'm not going to go into in this talk, but one of the features is we add a service name. One of the common problems in our logs is in Elasticsearch, you map a service name to some magic index pattern. While this is good, a lot of people during an incident who are not familiar with your service do not know what that service pattern is, and it's kind of hard to find the logs. So one of the things we do on ingestion is for every log that we ingest, we actually add a service name tag. That way, people can actually just use the service name tag to find the logs for the right service. And finally, in summary, the current status of KalDB is we are building it as an open source project in the open. Currently, our KalDB cluster handles the largest Elasticsearch cluster we run at Slack, which ingests at about 700 Mbps peak ingest capacity. We currently can create recovery tasks and handle them to handle log spikes. We have very low operational overhead. It's already deployed on Kubernetes, and we have replaced the entire cluster several times since without human intervention. We handle field conflicts automatically. This cluster manages about 300 terabytes of data. We have a bigger cluster coming up. We ingest about 4 million messages per second, and that's the peak ingest capacity of 700 Mbps right now. And in future, we are going to do a beta release later in this year for everyone to use. Currently, the query API is basic API for the Kibana front page, but in future, we want to add richer aggregations and also provide a Kibana compatible API so our users do not see any difference between this system and the existing system. Further, we actually want to do more performance and stability improvements as we go forward. We also have a big vision of unifying logs and traces into the same system in the future. Our project on GitHub is slackhq/KalDB. Please check it out. We are looking for contributors and design partners. And in summary, running Elasticsearch at scale is a challenge, so we built a disaggregated storage architecture. We built KalDB using the disaggregated storage architecture that provides tied availability, separates compute and storage, separates durability from storage, and it runs on Kubernetes. It helps with Slack enable smart growth where we can actually, it's easy to scale the system and operate it. It takes minimum ongoing investment for us, and it prioritizes fresh logs over older logs. So during an incident, we actually know what is going on. And hopefully all of this combines into a lower total cost of operation, not just in infrastructure, but in developer time. This is the observability team at Slack. A lot of people are here. Please say hi. And thank you very much for your time and the opportunity.
Awesome. We've got time for some questions right up front.
That was a really dense talk with a lot of information. I feel like one of the densest moments was when you said we use Zookeeper. Can you talk about making that choice in this era?
Just repeat the question.
Yeah, so the question is, why do you use Zookeeper in this era? So the thing is, you need like two things, a persistent store and a notification store. And Zookeeper is the most scalable, persistent, and metadata store that is available today outside of doing two separate systems. There are other technologies that are much harder, but Zookeeper is something we already run for Kafka, we already run for Solar. I mean, it's bad at a certain scale, but as long as, so we try to design the system not to hit those scale limits, but yeah, it's like the best choice of the worst ones, you can say.
I feel like bad at a certain scale is a good description for pretty much all technology. Any other questions? Well, we got a bunch. All right, how about the closer one, and then we'll get the one behind. Yep. Yeah, sorry.
Just a question. Can you query different indexers and aggregate results over different indexers?
So the question is, can you query different indexers and aggregate queries over different indexers? The answer to that is yes. The query service can actually query different indexers and then aggregate data over different indexers and provide a result. So you can actually query across services. Cool.
My question is regarding, well, your system, it seems like it's optimized for more short-term analysis. For like longer-term analysis, like at the scale of like years or something, like a year of data, or months, right? What thought have you guys put into that, how you would approach that with y'all's database?
Yeah, so that's a great question. So for long-term analytics, currently we say that our data warehouses is the best option. And the reason for that is kind of twofold. The first reason for that is in this system, you actually move the data and then you send computation to the data. So the data actually has to be warm to be able to query it. And that costs money. Now, for longer term data, you can definitely get the data into the same system and query it. It'll be expensive and possibly slow. With data warehouses, what they do is they just keep all the data in S3 and only download the chunks in an incremental fashion, and it's cheaper. Can you do longer term analysis? Yes, but also it depends on the scale you're talking about. If you only have 10 terabytes of data for years, it really doesn't matter which system. Like you can, yes, put this in this system. But if you have collecting 100 to 200 terabytes of data a day, and then you're trying to do like a year's worth of analysis, that's a lot of infrastructure costs that you need to think about. Like the cost benefit of how you design the system actually matters at that scale.
Thank you.
Could you explain why your primary indexer is only single-threaded as it's moving through all the data? If you've shown that in the recovery task, you can't have multiple threads to catch up, and when you're horizontally scaling, if you've shown that there are top of main indexer with multiple threads, is there a reason why you're not doing that?
Yeah, so one of the reasons we only need a single indexing thread is Lucene is actually pretty efficient. So doing multi-threaded indexing is not needed. You only beyond, let's say 3 or 4 Mbps is when you need to start in like getting into multi-threaded things. So that's why we keep we don't need that much indexing capacity in the indexer. That's one reason. The second reason is even if you could ingest more faster, your chunk size will be pretty big. So if the blast radius of a failure is pretty high, so this helps us also limit the blast radius. And the other advantage of just having a single-threaded indexer is you can actually, generally a single thread actually uses one core. So it's much more easier to plan mentally on, when you scale it up and scale it down, it's much more easier to plan how to scale the system. So there are like advantages like that operationally, and that's why we just stick with one thread. But other than that reason, there is no other reason you can do multiple threads.
Great. Were there any questions over on this side or up top? We got them all. Oh wait, no, we got some more. I'm missing it. The aisle there. Yeah.
So the question is, can you talk about the cost comparison with Elastic? So we are currently, like, we put this system in production. We are roughly similar in cost right now. That's because of some of the things that are more tied to our infrastructure than the implementation itself. But we are actually hoping that the system is significantly cheaper because we are not keeping older data and we only load the data on demand and things like that. We don't do all of those yet, but that's the plan in like the next few months.
I think there's one over here, right? Yeah. Oh, same question. Gotcha. All righty. Great. Thank you very much. Another round of applause.